Dear students, today we'll study about the hydrothermal scheduling process. Here in the hydrothermal scheduling, we are having two types of the processes. One, it will be for long-term hydrothermal scheduling, and another one is the short-term hydrothermal scheduling process. Here in this session, we'll discuss about the short-term hydrothermal scheduling process using y-lamda iteration method. Here in this method, the mathematical model, whatever they are going to build up, it is slightly different in terms of the constraints what you are having. The problem with regards to the short-term hydrothermal scheduling process using y-lamda iteration method, it is defined as minimize f of t is equal to summation from k is equal to 1 to n h raised to k into f of pgt raised to k. In the discrete hydrothermal scheduling process, we are taking only f of t is equal to f of pgt raised to k. But here in the short-term hydrothermal scheduling process, we are taking h raised to k also, wherein this h is nothing but what? It is the head of the hydroelectric power plant. So this you name it as equation number 1. So in equation number 2, we are taking it as summation from k is equal to 1 to n. So q naught raised to k into h raised to k is equal to q total. So whatever the total quantity of the water which is available, so that will be the multiplication of the discharge and the total head of the power plant. So here we need to solve the coordination equation for this reason. So we need to compute the following equations now. What are those equations? The differentiation of the function of pgt raised to k divided by pgt raised to k. So here this is the general cost function of the thermal power plant, wherein it is given by f, that is function pgt raised to k is equal to at plus pt into pgt plus ct into pgt square, wherein at, bt and this ct, they are the constant with respect to the hydrothermal scheduling process. And already you know pgt is nothing but what? It is the total power which is generated from thermal power plant. This you take it as equation number 3, wherein if you do the differentiation with respect to this equation, so differentiation of the function of the total power generated divided by the total power generated with respect to the kth unit, that will be given as bt plus 2 into ct of pgt. Where this a vanishes, this a is nothing but what? Will be a constant. So the differentiation of any constant, it will be 0. So the equation number 4, it will be only written with bt plus 2 ct of pgt is equal to the total function. So here the discharge q naught raised to k is a function of pgh raised to k. So whatever the q naught raised to k you are having, it will be a function of pgh raised to k, that is the total power which is generated from hydro power plant at a kth interval. So that differentiation, it can be given as q naught raised to k is equal to ah plus bh plus pgh. That is, this equation holds good for the generation if it is below some limit. That is, if you are going to fix up one limit, then the generation is below the limit, then we are calling it as ah plus bh of pgh. Okay. So if generation is above the limit what you are going to fix up, then ch of pgh square parameter will be added. So the equation will become ah plus bh of pgh plus ch of pgh square. So this will be the equation for q naught. And by seeing the input and output characteristics of the hydro power plant, so this x-axis, it is there with respect to the power generation with respect to hydro power plant in megawatt, and this y-axis we are having it for the total discharge in terms of meter cube per second. So this curve indicates it is the total discharge with respect to the total hydro generation what we are having with respect to the system. So the third point is, here we need to have the loss coefficient equation again. So the loss coefficient equation, it is given as BTT of PGT K square plus 2 BTH of PGT plus into PGHK plus BHH of PGHK raised to 2. If you go for the partial differentiation of this, then partial differentiation of the loss component with respect to PGT, here see it carefully, partial differentiation of the loss component with respect to only PGT parameter, that is power generation with respect to the thermal power plant. So it is given by 2 then BTT to BTT of PGT raised to K, 2 BTT of PGT raised to K plus 2 BTH of PGH, 2 BTH of PGH. So this complete BHH term, it will vanish here. Then if you are considering the partial differentiation with respect to hydro power plant, then the equation will be 2 BHH of PGH raised to K, this equation will come, and plus 2 BTH of PGT raised to K. This equation will be vanished in your second equation, that is equation number 8. So coming to the algorithm of this short-term hydrothermal scheduling using y-lamda iteration method. First up is choose epsilon 1, the tolerance for power mismatch, and epsilon 2 is the tolerance for the total water discharge. What is that? Epsilon 1 is the tolerance for power mismatch and epsilon 2 is the tolerance for water discharge. First you have to choose them, that is you have to select epsilon 1 and epsilon 2. Then after that select the initial values of y and lambda raised to k. You have to select the initial values of y and you have to select the initial values of lambda raised to k. Then assume initially all the generation are at 0, means the generation is not there in that particular system. At this condition, by assuming epsilon 1, epsilon 2, y and lambda raised to k, so what you need to do is you need to set the value for k is equal to 1, that is for first time interval of that operation. By setting that k is equal to 1, what you need to do, you need to calculate the PGT raised to k using the coordination equation. The coordination equation for PGT raised to k can be given as h raised to k into BT plus 2 CT of PGT raised to k plus lambda raised to k of 2 BTT of PGT raised to k plus 2 BTH of PGH raised to k. That will be equal to lambda raised to k. Suppose if you want the equation or if you want to derive the equation for PGT raised to k, then this will be your equation, that is lambda raised to k minus hk into bt minus 2 lambda raised to k into bth into pgh raised to k divided by 2 hk ct plus 2 lambda k bt. This will be your equation for pgt raised to k. Then after deriving pgt raised to k, then you need to derive the equation for pgh raised to k. Here the equation will be lambda k minus y h raised to k into btt ph minus 2 lambda raised to k into bth into pgt raised to k divided by 2 lambda k into bhh. And after calculating this, you need to calculate delta pk, that is change in the generation with respect to the hydro and thermal in the kth interval. So that can be calculated as PD raised to k plus P loss raised to k. That is, you have to add both losses and the total load demand of the consumers and subtract it with PGT raised to k minus PGH raised to k. You will get the total value of delta pk. And after that, if delta pk is greater than, less than or equal to epsilon 1, then at that time calculate q naught k. Or if then k is equal to 1, that is for the last time interval. If k equal to k plus 1 and go to step number 4. If k is equal to n, if not k is equal to k plus 1, then at that time go to step number 4. Or once q naught has been computed for k is equal to 1 to n, check if delta q is equal to summation from k is equal to n q naught k hk minus q total is less than or equal to epsilon 2 or not. If yes, stop the iteration here only. If no, then magnitude of delta q, if it is greater than epsilon 2, let y is equal to y plus delta, that is the total change in that particular system. If y is positive, if delta q is positive and negative, if delta q is negative, then go for step number 4, or otherwise we continue the loop iteration for y minus lambda until delta p and delta q have the convergence. Here in the flow chart is nothing but what? It is the pictorial representation whatever we are having for that particular algorithm. So flow chart starts with the selecting the initial values of lambda raised to k, y, then pgt raised to k and pgh raised to k. And here also you have to determine the values for epsilon 1 and epsilon 2. After selecting the initial values, then set k is equal to 1. And for k is equal to 1, solve for pgt and pgh and calculate the total power loss. That is, you have to calculate pgt, pgh and total power loss. After calculating this one, then go for calculation of delta pk, that is pd raised to k plus p loss raised to k minus pgt raised to k minus pgh raised to k. This gives you the total change in the power with respect to the kth interval. If delta p raised to k is less than or equal to epsilon 1, then find q naught raised to k. If not, then go for the calculation of lambda raised to k is equal to lambda k plus delta lambda k. If this is calculated, then again this step will be repeated from step number 3. Or otherwise, if it is calculating the q naught raised to k, then check whether k is equal to n or 1. If k is equal to n, then calculate the value for delta q. Delta q is equal to summation from k is equal to 1 to n h raised to k q naught raised to k minus q total. If this is calculated once, then check whether magnitude of delta q is less than or equal to epsilon 1 or 1. If it is less than or equal to epsilon 1, then go for the scheduling of the outputs. If no, then go for the calculation of y is equal to y plus delta y. And after calculation of this, again this step will be repeated from step number 3. And if this k is not equal to n, then at that time what you need to do, you need to calculate k is equal to k plus 1. Then again this step will repeat for solving the problem. This is what the short-term hydrothermal scheduling using y-lamda iteration method.